So first of all, thank you for inviting me to this conference. It's very interesting to me. Although my topic is not directly related to SystemC, I think it's still fitting quite well. So today I want to present you our QEMU-based fault effect analysis for RISC-V microprocessors. And just for the terminology, we all know about test benching. We have test vectors on the left side. We have our hardware under test, and also we have our monitored responses. And we do that to figure out if our hardware is faulty, and we do that by comparing the output of a fault-free hardware with our hardware under test. With regard to the input from the test vectors. So this is what we use by test benching. So so in general, we say that a test vector is good if it's triggering a faulty behavior or faulty behavior that's seen on the response side. So if we can, if we compare the output with the golden output, the test vector is considered to be good if the output differs. The other way around, test vector is bad or useless if the monitored response is the same. For RISC-V, we have a slightly different terminology. We do not speak about test vectors there. Instead, we call our test vectors RISC-V test software. On the right side, we don't have responses, not the general term, but instead we have exit codes or exit conditions that come from the software execution. And in the middle, we don't have the abstract term hardware under test. Instead, we have the QEMU RISC-V hardware. The idea is still the same. We have a golden RISC-V CPU, which produces golden exit codes. And we also have, and then we inject faults into copies of the golden model where we break something. That's what we call fault injection here in this case also. And then we just compare the exit codes of the golden and the fault injected versions. So our fault model for the RISC-V CPUs is as follows. RISC-V has different, like any other CPU, it has instructions that are executed. It has some sorts of general purpose registers and some configuration registers. Configuration registers, for example, for the core itself, like PLL settings, and maybe you can think of a lot. It's highly dependent on the actual implementation. And also we have memory mapped CSRs. Those are for configuring attached peripheral devices. They are memory mapped. And also we are investigating faults in memories, including memory mapped I/O. So not physical memory, but instead some peripherals that are connected via the memory bus. And we do this analysis, or the fault model is based on bit level. So for each and every instruction and for each and every registered memory, we modeled bit faults for RISC-V. So that's the basic idea. Okay, when we are talking about permanent faults, those are time independent. This means that, for example, for instructions, which are 32 bits wide, we would have 32 single bit faults per type of instruction or per instance of instruction in the software, for example. For GPR faults, RISC-V defines 31 registers with 32 bits each. So for GPR faults, we have 32 times 31 single bit faults, 992. Similarly, we can do this for CSRs. The amount of control and status registers is highly implementation specific, so there's just a formula, but it's still quite easy to calculate. For memories, we treat the memory in general as a collection of bytes, and for each byte, then we just count each and every bit fault as one of the 8 bits in each byte. It gets more complicated when we are talking about transient faults, because transient faults are time dependent. And this means that over time, we will get more and more faults to simulate. To get a little bit more concrete, for example, for instructions, we now have to consider each and every execution of an instruction. For example, if we have some calculation inside a loop, we would need to simulate a single bit fault in one of the instruction types, for example, an add inside of the loop, for each and every execution of this add instruction. So you can already guess that we will end up with lots of transient faults that are to be simulated. And this is only for single bit faults. It explodes even more if we drop the single fault assumption or go to multi-bit simulations. So this is just a main takeaway: transient faults explode because each and every execution creates a separate mutation that we need to test. Okay, so for our approach, we call it the fault effect analysis for RISC-V, or abbreviated FEAR-5, and it works in 4 phases. So the first phase is basically the generation of the test vectors, or as we call them, test software. So there is already test software available, which we call libraries. We can also generate software and compile it. In the next step, when we have the software, we have to do some analyses, which we call the golden run and hardware execution analysis. This serves as the input for the third step, which we call mutant generation with fault injection. And last not least, we simulate the faults and perform some analyses and optimization. Our approach is highly configurable in terms of RISC-V instruction set modules. There are different modules, for example, like if you want floating point support or not. You can also configure if there should be an iterative optimization of the test software, whether you want single or multi-bit fault simulation, transient or permanent faults, and so on. So let's get started. The first step, as I already told you, is software generation and compilation. And this divides into 2 areas. First of all, we found some generators which we can use. For example, CSmith. I'm not sure if any one of you knows it. It's an NCC code generator from University of Utah, and it's meant primarily for compiler testing. So you can then basically run the same software in different compilers and check whether, for example, GCC behaves differently than LLVM. This is one of the generators that we use. We also use the Torture software generator. This is an assembly generator especially made for RISC-V. And additionally, we use some test libraries. This is basically what we call static software. So that's not dynamically generated, it's just floating around. We use it and simulate it. The first is the set of RISC-V tests, which is a collection of assembly test programs released by the University of California, Berkeley, and now is managed by the RISC-V Foundation. Also, there are software tests from the RISC-V Foundation Architecture Test Group. They were formerly called RISC-V Compliance Tests. And thirdly, we designed some hardware handwritten tests for status register bit fault investigations. And we compiled everything with RISC-V GCC. So this is for the software generation and compilation bit. Now coming closer to the interesting bit, after having generated the software or compiled existing software, we put this software into QEMU and let it run. And we extended QEMU in a way that we are able to collect a lot of data during the execution. And we call that the golden run with hardware execution analysis. Some questions that are answered by this golden run analysis contain questions like which and how many instructions are executed. For example, does our program contain specific branches or not? Or how often are specific branches being performed? Additionally, we can monitor how often and when registers are being executed. So, for example, GPRs, how often is the third GPR being read or written? And additional properties include, for example, the number of executed instructions, the number of instruction words inside of the program memory, which corresponds to the lines of code, if you like. Also, we measure program execution time and we monitor accesses to each and every memory byte. On the right, you can see an example table that basically shows you 7 CSmith programs for RISC-V for a specific subset, which is called RV32GC, which is basically the standard 32-bit instruction set for RISC-V. It includes floating point, and it's just an abstract description of how which features from the modular RISC-V instruction set are used. So in this case, this example refers to RV32GC. So the table shows you, for example, how many of the defined instructions are being covered by the different programs. For example, the program 6 covers more instructions, different instructions than program 5. This is what you can see here. Also, from the 32 GPRs that are available, none of these 7 programs uses each and every of them, but some use 30, some use 27, and so on. We can do similar investigations for CSRs. This is the second to last line, and also we can investigate the lines of code. This is just to give you an example about the golden run execution analysis. In the third step, we use the information from the golden run hardware execution analysis, and we use this information to then derive the faults that we want to inject. So we can also use it to determine already how many faults we want to simulate, and this is then how we can also estimate our fault simulation time. And yeah, the main bit is here at this point. We inject permanent or transient bit faults, single or multi-bit, with respect to what the user wants. So it's you can configure this. And we are able to generate and inject permanent and transient n-bit faults into instructions. Also just to specific bits, if you like, for example, only to opcodes or only to operands, into registers like the general purpose registers, also to the configuration registers, and last but not least, the memory, including memory mapped I/O peripheral devices. Right here, we already discovered some possibilities to reduce the amount of mutations to reduce the simulation time. For example, we can skip mutants that would affect hardware that's not being used by the test software. For example, if we have a test software that doesn't use the general purpose register 1, it doesn't make any sense to simulate this software with a fault injected CPU which has the fault injection in register 1. Similarly, we can reduce or discard mutants that access invalid memory. So we know the memory layout, and also we know if the system under test, the RISC-V CPU under test, introduced a memory protection unit or a memory management unit. And so we can then decide whether a hardware memory access, a load or store, with a base value in a GPR and offset that's encoded in the instruction will point to valid RAM or to invalid. So in the case that a fault injection, which basically inverted the red bit here in the GPR selector, leads to a memory pointer that points then to invalid memory, we can discard this particular mutant. To give you an example for both of these techniques, I already showed you in one of the CSmith programs that those only accessed or executed 30 out of 31 general purpose registers at maximum. So this means for such a program, we wouldn't need to actually simulate all 992 permanent GPR mutations, but only 960. For the memory protection example, just consider a software that has roughly 2 million GPR executions, from which 1.5 million, 1.6 million are load and store instructions for invalid memory. We saw that actually in our examples. So we assumed that we had a memory protection configuration that was rather strict with regard to accesses to memory that's not being owned by the small test software. So in this scenario, we were able to reduce the 1.9 million possible mutations to only 0.3 millions. So this means that only 17% of the mutations actually need to be simulated. So this is a huge opportunity to save simulation time without losing accuracy. And coming to the fourth step, which is fault simulation and analysis. In this step, we simulate the list of mutants that we had generated in the previous step, and which was also reduced in that step. And we monitor then the exit code for each mutant. So coming back to the very first slide where we have the test benching, we have now as input a test software, and we simulate the test software for each and every mutant that we still have after the reduction. And then we monitor the exit code behavior and store all that in a database. So coming to the exit codes, there are basically three groups of exit codes. One would be that we introduce endless loops with the injected fault. So for example, we might alter a branch in such a way that a loop is never being exited. This could be detected by a watchdog, so we consider this to be, let's say, a good mutation to detect this specific fault. Another exit code group we call killed, because a mutation is being said to be killed if the mutation was detected. And this splits up into two groups. First of all, if we break something with a bit mutation in the CPU, we might end up with a so-called RISC-V standard exception. A standard exception might be, for example, unaligned memory access, or we might even have an illegal instruction that's not defined in the instruction set architecture at all. So those two, and also more of the examples here in the list, would result in an exit code that's not normal, but instead shows you that something terribly happened. So this is the good case, which means your test software is able to detect a bit error in this specific position, or for this specific scenario. The bad case is if we cannot kill a specific mutant. This means, or this is equivalent to the bad case in the test bench slide, where I told you that a test software is bad if it cannot detect a fault in a way that you can see different output. Yeah. So our FEAR5 approach now allows you not only to measure the exit codes of all the mutations, but also answer questions like how many of all mutations were killed or not killed, how many of those mutations ended up as a timeout, and so on. For the not killed, it might be interesting for the user, for the system developer of the RISC-V CPU that uses FEAR5 for development or for testing, which not killed mutants, how the not killed mutants distribute onto different injected faults. For example, in this example, we have roughly 240,000 not killed mutations. And on the right table, we can see that, for example, 468 of those were related to permanent GPR faults. And we can even ask more specific questions. You can then find out that one specific not killed mutation was related to a specific fault into one register at a specific point in time. Okay. So now coming to an example. I hope you're not shocked by this big table. I will skip most bits of the table. It's just to demonstrate how much information we can gather. The top table shows you a list of 24. So first of all, I'm talking about 24 test programs that were generated by the assembly software generator RISC-V Torture. And we apply this to a Sci-Fi Freedom E300, which is an FPGA version of the Sci-Fi Freedom E310, which is located on the Hi5 board, which is quite popular. So I assume some of you might know it. So in those two tables, you see the 24 test programs and how they behaved in the golden run phase and also in the mutation test phase. What's interesting here is especially the total amount of instruction executions in the golden case, which is the bluely highlighted line. And also for each and every program, we get a specific exit code. So it's here grouped as killed and yeah, in the killed and not killed bits. But as I already told you, if you are interested, you can expand this table to way more details. Yeah, the main takeaway, what I want to show you is now that in this example, we already had roughly 20 million instruction executions if we just simulate programs one after another without any fault simulation. Additionally, in our test configuration, in this specific example, we generated 1 million mutations. And putting those numbers together, we end up with a highly we can parallelize this approach quite well, because simulating program 1, for example, is completely different from simulating program 2. So the complete test run of program 1 could be simulated in parallel to programs 2 to 24. And on my simulation machine, which has 12 cores, 24 threads, we end up with a very fast simulation speed of close to 4,000 MIPS with fault simulation enabled. So in this particular example, the real time was 229 seconds. Yeah, if you would just simulate it onto a single core, you eat close to 20 times as much time. So it's very, very easy to exploit parallelization here. Okay, putting it all together. I briefly showed you our fault effect analysis for RISC-V testing framework. It's based on QEMU, and it incorporates existing software libraries, handwritten tests from ourselves, and also we provide a generation front end that allows to use and configure RISC-V torture and CSmith. It's highly configurable with YAML files, and in those YAML files you can specify, for example, which instruction set architecture subsets or modules are about to be simulated or are available in your test hardware. For example, you can then specify whether the virtual QEMU CPU should support floating point instructions or not, whether it should incorporate privilege levels like machine and user modes and so on. Additionally, you can specify the amount of bit faults. So if you would like to stick to single bit faults, or if you want to go up to n bit faults, it's up to you. It's only limited by simulation time. Additionally, you can specify whether you want to use a bitflip fault model or a stuck at a 1 or 0 fault model, whether you want to simulate transient or permanent faults or both, and so on. So this all you can specify in the YAML file. The last takeaway for Fika 5 is that it's really fast, and it's in the state that I just showed you already fast enough for 2-bit faults. If you limit the 2-bit faults to be in the same resource, for example, in the same instruction or in the same register. It's fast enough for transient faults. Let's say not in every case, but it's so fast that for some scenarios you can do transient fault simulations. And it's fast enough to do an evolutionary approach to iterate over and over again to gradually improve the test software that you've found so far. The outlook. What we are currently working on is the chip layout dependent fault generation. What we mean by that is we synthesized the Freedom E CPU in this example with Innovus, and we looked at the standard cell layout. And from the standard cell layout, we then get information about the neighborhood of flip-flops that belong to the same registers. And this information then we feed back into the Fika 5 approach to only consider multi-bit faults that are meaningful. Meaningful in terms, you can think of single event offsets, and they will probably hit adjacent cells, but not cells that are quite far away from each other. So this is the idea of the chip layout dependent fault generation. There we are currently working on it, and I'm quite sure that in the near future we can show you more results. Okay, that was it from my side, and I'm now happy to answer your questions.
Thank you, Per. Thank you.
I hope I wasn't too fast, but it's very much information in very short time.
Yeah, I can start. I put a question here in the chat. I was just curious if you modify the QEMU in some way. So
yeah, I'm modified.
When you translate a faulty instruction, do you also generate a faulty x86 instruction, or how does that work?
Yeah, I expected such a question. This is an image of drawing from one of our papers back from 2016, where we implemented permanent fault injection into the tri-core version of QEMU, but the target is not relevant here. So between the fetch and the decode phase, we modified the bit of the tiny code generator in QEMU to transparently mutate instruction words before they are decoded and translated. Does this answer your question?
Yes.
Okay, perfect. So to go into more details, maybe for register fault injection, you can introduce so-called helper instructions in the tiny code generator, and those we use for transient simulation of register faults.
Another question, you mentioned at some point in your talk that you had some board or some hardware. I didn't get that. Did you suddenly run on real hardware or?
No, we decided to stick to the Sci-5 Freedom E platform because it's quite popular and it's has a quite well support in QEMU. And additionally, the RTL is available, so we were able to simulate, to synthesize and do a place and route for the chip layout analysis.
Okay.
And also there's free hardware, or the hardware is available. You can buy it, and there is the so-called Hi5 board, which I think was the first commercially available RISC-V board on the market. So this was the intention of using the Sci-5 environment.
So you're trying to map sort of realistic fault scenarios in real ASICs and back to your simulation, right?
Yeah, exactly. So we want to exploit the high simulation speed from QEMU and combine it with a very close look on the physical circumstances.
Yeah, very interesting.
Of course, we have some limitations on the other side. We are quite fast, but not as accurate in terms of timing. But I suppose you already know.
More questions? Anyone? I can just make a little comment on the QEMU. You wondered if the QEMU was the right topic for this meeting, but we have actually had QEMU here before, and we have had talks about QEMU mixed with SystemC.
Are you from GreenSox?
Yes.
Okay, so yeah, I never worked with QBox, but I did some research when I started working with Wolfgang Müller. So he told me about it, and it's really interesting. But
you can say hello to him because he is in this meeting, Mark Burton.
You can say hello to me, yeah. But there should be some more news about QBox and stuff. I've just literally this minute got back from KVM forum, where it was also the topic of a lot of discussion. So yeah, there's probably going to be some movement in that particular space.
Yeah, I see huge possibilities with the new plugin API for QEMU, but there's one big drawback. As far as I know, you can only monitor the system state, but you cannot alter it.
Yeah, actually, it would be interesting to have a way of injecting through.
Exactly. That's what I mean.
And your use case is a very interesting case in point. Yeah, at some point, drop me. This is Mark, so I'm mburton@qti.qualcomm.com nowadays. But yeah, drop me a message, and we should sync up on that and see what we can do to improve the QEMU API.
Yeah, sure. That's thank you. Yeah, I'll do that. So, any more questions?
Perhaps not. Then we should say thanks to you, Per, again. By the way, my second name is also Per, but with one E.
What a coincidence. I never met Per by myself. I know pairs from television, but I've never...
There's a few of them in Sweden. Yeah.
Hi.